Very good. Hello. Uh, Very good. One of the driving forces behind this course is the fact that once you have a new understanding of what probabilities are, that immediately forces you to see if you can have how this new understanding affects your understanding of physics. Uh, Probabilities appear in physics in several different places. One of them is when you're trying to compare experiments to theory, there are always experimental errors, right? So that's one of the big parts of physics. Compare theory with experiment. There you have experimental errors. You need probability theory. Another is in statistical mechanics. You have a bunch of atoms doing wacky things. There are too many of them to keep track of them, and so you end up using probabilistic arguments to take into account that you do not follow all of their trajectories. So statistical mechanics. We have seen a little bit of how data analysis would go. Very little there. We have seen a fair amount more of how to apply these new ideas to statistical mechanics. What I want to pursue from now on to the rest of this, throughout the rest of the course, is to tackle the other subject where probabilities appear in a very prominent way, which is quantum mechanics. So one of the crucial features of quantum mechanics is that it involves evolution in time. Now, nothing we have said in the theory of probability leads us to make any assertions about time. In other words, the theory of probability is completely silent on the issue of time. It's atemporal. It allows you to make predictions of the future and also make assessments about what happened in the past or maybe in the present. It's just a matter of handling uncertainty. So one of the things we're going to have to do is figure out very carefully how time is going to enter in a theory that's supposed to be purely inferential in nature. That's going to be for the next chapter. In this chapter, we want to set the background foundations for how to even get started doing that. One of the aspects that we want to study, therefore, is what happens when you have a space of probabilities, a statistical manifold, and you want to move there. You want to move on this space. That would be a time evolution. Well, before we study a time evolution, let's just study, you have a space, and you want to study curves. See where that takes us. Very good. In order to do that, I have to start drawing pictures. So one of the things that we're going to have is a space, a statistical manifold, and we're interested in studying curves. The curves are going to be parameterized by some parameter. Eventually, a special case of this parameter might end up being time, but for now, it's just parameters. And so a curve, well, you're going to have curves. If you have curves, as we saw when we're studying information geometry, you're also going to have vectors. So we would like to be able to study the nature of vectors on these spaces. Vectors are important because eventually they will help us understand things like velocities. The other thing that we're going to have to introduce are covectors, also known as covariant vectors or one-forms. And the reason we need the covectors is that they are the ones that are going to describe things that we're going to find very useful, and that's momenta. We're going to have coordinates, and we're going to have the conjugate momenta. Where do momenta come from? They're just covectors in these spaces. Very good. To simplify life, so, okay, yes. One of the important aspects of what's going on with curves on these statistical manifolds is that a point on such a space is not just something completely structureless. So we're not just talking about curves and points on manifolds of a generic nature. We're talking about points that represent probability distributions, curves that represent evolving or changing probability distributions, and these manifolds come with a metric structure. They have their information geometry is already supplied for us. So we want to study special families of curves that are particularly suited to the fact that we have definite metrics on these manifolds. So let's try to put all that together, and by the end of this set of like maybe 3 lectures here, we're going to get to Hilbert spaces, complex numbers, and a bunch of other things. So all of that before we actually do quantum mechanics, just geometric backgrounds for curves on statistical manifolds. Very good. To simplify life, we're going to consider statistical manifolds that are of a particularly simple nature. We're going to consider discrete manifolds, discrete probabilities, or rather discrete microstates. I takes values 1 through n. The corresponding probabilities are the probability of I, and we're going to set some coordinates on this space. And so what we're going to do is we're going to choose as special coordinates the values of the probabilities themselves. So we're going to write this as theta I. So what this space here, we've seen this kind of spaces before. The statistical manifold is called a simplex. It's called a simplex. The simplex theta, it's we're calling it S. The simplex S is going to be the set of all probability distributions such that we're going to take these probabilities to be positive. It's a good idea to avoid the zero. You can always take the limit theta going to 0 if you want. And we want these guys to be normalized. This is equal to 1. So that's what a simplex is. The simplest example is something in which the normalization condition here gives you a set of points where here we have probability of 1, probability of 2, probability of 3. The axes are like so. This is what would represent, this is the two-dimensional simplex. And it could represent a 3-sided die. Very good. So you may as well just think about the two simplex, a 3-sided die all throughout. We're going to do this for n dimensions, 1, 2, 3, 4, 5, and to n. So what we're going to be dealing here with is the n minus 1 simplex. We could write it like this. So this is an n minus 1 simplex. Very good. This is the space on which we're going to draw curves. In order to be able to do all of this, we're going to have to take derivatives. So our next topic is the issue of Lie derivatives. Why do we need some fancy notion of derivative here? Okay, the problem is the following. If you have a curved space, and we've seen this before, uh, tangent vectors live on a tangent space here. On a different tangent space, you have a completely different space of vectors. So one of the things that becomes clear once you have tangent spaces that are different at different points is that you cannot take differences of these vectors because they live in different spaces. And so the issue of how you take derivatives of vectors or of tensors in general when they live in different tangent spaces becomes crucial. We need a fancier notion of derivative in order to be able to handle that. One of those notions is the covariant derivative. What we're going to need here is the Lie derivatives. The Lie derivatives end up functioning as this. Okay, so let's first go back and try to do our vectors. Remind ourselves how vectors work on this space. If you have a curve, so here you have, let's just write a generic curve space. You have a curve. A point here is labeled by index lambda. The equation for the curve is you give the coordinates as a function of lambda. And a vector, a tangent vector here, one that lives on the tangent space, would have coordinates, would have components in which you take the derivatives with respect to lambda. These are the components of the vector v, and we saw how to take derivatives of functions for this vector. So if f is a function on the statistical manifold, which in this case it's the simplex, then the derivatives, the directional derivatives, are going to be taken by taking derivatives of the function with respect to theta and then derivatives of theta with respect to lambda, which means we have the f d theta, something like that. Very good. This we could take in a couple of directions. One of them was to note that since f can be any function, we can identify this differential operator with the vector v, which has the same components, and these are going to be the basis vectors. So we can draw that identification. But now we can clean this up in a variety of ways. Let me see. Now that we have vectors, curves, and tangent vectors, you can imagine having a congruence, a space filling congruence of curves. What this means is the following. You have your space and you have curves. That's one curve. Here's another. There's another. There's another. There's another, and so on and so forth. The idea is that you have this family of curves that fills the whole space. That's called a congruence. Very good. At each point, you have tangent vectors. Everywhere you have tangent vectors. So associated to a congruence of curves, you have a field, a vector field, that means at each point in space you have, at each point theta, you have a particular vector. So if I give you a family of curves that fills the whole space, I can figure out the corresponding vector field. And conversely, given a vector field, we can integrate it. We can integrate, we can find the corresponding curves. We can find the integral curves. Basically, if I give you the vector field at every point, and by that I mean I'm giving you the components, then I can integrate these equations to find theta I as a function of lambda. So you can go for the vector field to the congruence of curves or vice versa. Now, why is this interesting? Because what we would like to be able to do is take any quantity, a scalar, a vector, a covector, a metric tensor, however, and we would like to be able to see how it is that it changes as we move along a congruence. So we want derivatives with respect to the vector field V. And this is what's going to take us to introduce the concept of the Lie derivative with respect to a vector field. So how does this work? So we're doing derivatives with respect to a vector field. The way this works is as follows. For scalar functions, let's do it first for scalar functions. For a scalar function, f, which is a function of theta, and here is the space, and here we have one of those integral curves. We're going to invent the following. If you have the function at the point theta, what we're going to do is we're going to figure out what happens with the function at the point theta lambda, where lambda, theta lambda is the point theta displaced along the curve by the parameter lambda. Very good. So now that we have this, it's the same function, right? Here we evaluate in one point, here we evaluate at a different point. Nothing bad, right? But now we're going to do something amusing. What we're going to do is we're going to say, look, if you have this function here evaluated at the point lambda, we're going to invent a new function at the point theta. The new function, we're going to call it f lambda, but it's evaluated at the point theta. And what we want is the new function f lambda at the point theta is equal to the function at the original point. So what we have done here is we've brought the value of f at this point theta lambda, we have brought it back to the point theta. This is called the pullback. But this is where the name pullback comes from. We have pulled back the function f at the point theta lambda to the point lambda. And now we can define the derivative. Then the derivative with respect to v of the function f is going to be defined as the limit as lambda goes to 0 of 1 over lambda of this pullback function minus the value at the original theta. You have this value and you have the pullback, right? And you subtract. Now, of course, you probably realize that since this value is the same as that, since these two are the same, what we're doing is we're taking the difference between those two and dividing by lambda, just a regular definition of derivative. There is nothing fancy here. But the particular way that we have written this down is interesting because the differences that we're taking here are differences at the same point theta. We're taking the difference between a function defined at the point theta and a function defined at the point theta. Not at two different points, but at the same point. In the case of taking the derivative of a scalar function, that's sort of trivial. It's not a big deal. It's what we expect. But if you were doing this for tensors or for vectors, if you were playing with vectors, you can still do the pullback, and we would be defining the derivative of the vectors that we're bringing back, pulling back. We're doing the derivative, but at the same tangent space. So then we would be, if these were vectors, we would be able to subtract two vectors in the same tangent space. That's well defined. Very good. So this is how you define the Lie derivative. Let us just figure out what it is. Since f lambda at the point theta is the same as f at the point theta, which is we're concerned with lambda going to 0. So this is just going to be the function. Well, this is the curve here. The curve is theta as a function of lambda. So this is going to be the function at the point lambda equals 0, which is, well, at the original point, plus the derivative d theta d lambda d lambda. So that's what this guy is. If we substitute, we do a Taylor expansion here, what we have is f theta plus the df d theta I. Just doing the Taylor expansion here. Take the derivative with respect to the argument, multiply by the displacement. This multiply by the displacement, d theta I d lambda d lambda. And now we can go ahead and substitute this object here. When we do that, the first term cancels out and we're left with the second term, d lambda. This is just lambda. There is not a lambda there. This is just, we're displacing by lambda, so the lambda is small, so that's what it is. So we just substitute here, and what we get, the Lie derivative of the function f is just going to be the derivative of the function with respect to theta, derivative of theta I with respect to lambda, multiplied by lambda and divided by lambda. So this is just the lambda. So this is not surprising at all. We sort of concocted these things. The derivative of a scalar function is the derivative of the scalar function. There are no surprises here. Note, however, that this Lie derivative is a scalar operator. You act with this object L on a scalar function, and you get another scalar function. LV is a scalar differential operator. So far, no surprises. What we're going to do next, oh yes, there is one thing that we may want to do here. This expression here, you can see that we can write this as d theta d lambda, that's just v, right? And then this is the basis vectors, and then there is f, right? So we can write this as v acting on f. So that's just standard reinterpretation of the order of those symbols. The Lie derivative of f with respect to a vector field v is the action of the vector field on f, or just the directional derivative. So you have many different ways to talk about these derivatives. Very good. So now we're going to continue and apply these notions to vectors and covectors and tensors, and we're going to keep going. And the bottom line is that this is actually very simple. The more difficult way, and perhaps the more rigorous way and all that, would be to draw, write down equations, definitions of what it means to take the derivative with respect to the vector field v of a vector field u, and we could try to do something analogous to what we have done here. It's perfectly doable. We won't. We're going to take a shortcut, and we're going to say that the bottom line is that Lie derivatives are derivatives. In other words, what we mean by a derivative is that these objects here satisfy a Leibniz rule. In other words, the action of a derivative on a product is by taking the derivative of the first times the second, and then the derivative of the second times the first. So taking proper account that you have to preserve the orders. So what we're going to have here is, for example, the Lie derivative of the vector with respect to the vector field of a scalar, and let me draw the scalar. The scalar here is going to be the action of a vector field u on f. This is just df d mu, where mu is the parameter along the curves defined by this vector field, right? So the action of the Lie derivative with respect to v on this scalar function is going to be, of course, just act with this vector field on the scalar function. No surprises there. Take derivative with respect to dd mu, take derivatives with respect to v. That's what's going to be. But we want to note here that what we want to stress is that this also supposed to satisfy a Leibniz rule. So this is going to be the derivative with respect to v of the vector u. Since this is a scalar operator, this is a vector itself, and this is going to act on the function f. And so this is going to be the derivative of LV acting on u, and then with f being left dangling. So what we're going to do is act with LV on f plus u acting on LV on f. And here you see that this is a vector acting on a scalar function. So this is the kind of thing that we're always going to insist. Whatever these Lie derivatives are, they are derivatives. So this is going to be, no, sorry, df, the mu, this is going to be the u acting on f is given by that. Very good. So let's do the derivatives of vectors now. Now we can do this. Why are we worrying so much about this? Basically because we want to be able to take derivatives on these funny spaces. Okay, and remember, you cannot just take derivatives if the two vectors are on different tangent spaces. You cannot subtract them, so you have to pull them back, do a pullback of one onto the space of the other, and then you can do it. That's what we're gonna do. But why would you need the derivatives in the first place? Well, you need to do calculus to study change, motion, anything. So that's why we need the derivatives. In particular, we're going to need to take derivatives of the metric tensor. We want to, and we're going to be coming back to this later and later, but the idea here is going to be, if you have a metric tensor defined on a space, which we do because these are statistical manifolds, we would like to find out what are those particular families of curves that as you move, the metric tensor does not change. If the metric tensor has any sort of symmetries, we would like to be able to preserve those symmetries as we move. Okay, so we're going to end up imposing that the derivatives vanish or some such beautiful condition on the particular vector flows that we're going to be studying. Very good, but let's now just try to keep on trying to figure out what kind of calculus we are inventing to do these things. So the Lie derivatives of vectors, like I said there, the Lie derivative of a scalar function. So we have here v has components d theta, u is another vector field which has components u dd theta. This is the guy that we can write as being, well, the curves are parameterized by lambda, so this guy is dd lambda, and this guy here is going to be, well, just a different parameter for a different family of curves. So you have like two congruences here, right? And you're trying to figure out the derivative of one relative to the other. Very good. This is going to be, let's just write it out. We write it in this way. Since uf is a scalar, we just say that v acting on the scalar function is just taking a derivative dd lambda. On the other hand, we know, because we have Leibniz rule, that this is going to be the derivative of u with respect to v acting on f plus the u acting on the derivative with respect to v of f. Now you appreciate what it is, why it is that this is going to work. We have two different expressions on the left-hand side. On the right-hand side, we can compute what this is, because this is dd mu and this is dd lambda. Nothing prevents us from taking derivatives of scalar functions. And on this side here, we again have a derivative of a scalar function, dd lambda, and here we have dd mu. We know how to do all of these things. So now what we're going to do is just equate the right-hand sides. When we equate the right-hand sides, let's just do that. The u acting on f is equal to LVU acting on F plus U. And this here, this LV acting on F, this is just V acting on F. So what this is telling you is that the Lie derivative of the vector U with respect to the vector field V is given by VU from the left-hand side minus UV, which is like a commutator. It is the Lie bracket of VU. And this is just commutation of the derivatives that we have written over there. dd lambda dd mu minus dd mu dd lambda. So this is the Lie bracket. So this is the definition. This is what we get for the Lie derivative of the vector U. We can actually go ahead and compute this explicitly just to see what it looks like. Oh, before we do that, notice that because this is in the form of a commutator, the bracket is anti-symmetric, then we immediately get that the derivative of the vector field V with respect to U is minus the derivative of U with respect to V. What else can we do here? Okay, now yes. Next thing we evaluate. Let's evaluate these two guys separately. Let's do V U acting on F. And what this is going to be is when I do the first V is this derivative where this notation, I'm using this notation here. This acts on Uj, dj acting on F. And if I expand this thing properly, what I'm going to have is Vi, the derivative, these are just functions now, so taking derivatives is just taking partial derivatives the usual way. So I'm going to differentiate the first and differentiate the second. There, that's the first term, plus the second term, Vi. Now there is a Uj, there is Di, dj, F. Okay, so now we have done Vu. Now, next we do Uv in the opposite order. And this just consists in exchanging V's and U's here. So we're going to have U, yes, just du, I, V, J, dj, F, plus U, I, V, J, di, dj, F, subtract L, V, U is going to be acting on F, is going to be, just take the difference here, V, U minus U, V acting on F. And when we do that, you see that these two terms here, the second term and the second term, they're exactly the same, right? Nothing prevents you, because these are just numbers now, to commute these two, put the V on this side, and so it looks exactly the same as they do here, except that the V's come with an I and the U's come with a J. But these are dummy indices. You can always just relabel, change I's and J's. After all, I is being summed over all its values. J is being summed over all its values. Nothing prevents you from calling this guy J and the other guy I. When you do that, these two cancel out. And so what we get is the following. Vi, di, uj, dj, f minus ui di vj dj f. This guy and that guy are common factors, so let's pull them together. Let me get this guy out and bring it out here. F. Very good. Next, I'm going to notice that what we have here is the action of whatever this is on a function is a bunch of numbers multiplied by the derivative of the function, right? If I say that, since I notice that this is exactly the same expression no matter what the function f is arbitrary, then whatever this is acting on f is going to be the same as this guy minus ui I vj, all acting on this particular derivative. It's that derivative. This is j. Conclusion. This object is a bunch of numbers multiplied by a basis vector. So what this means is that this is a vector with components L, V, U. This was J, so the components J are given by VI, DI, UJ minus UI derivative I, VJ. In other words, this is again evidence that we used it to derive this, so it's not a surprise. This is a scalar differential operator. When this scalar acts on a vector, it produces a vector. There you see the basis vectors. So this is the final expression. Now, what do we have here? Next, we're going to do the same thing for covectors and for gradients. So let's repeat this. And in order to do the Lie derivatives of covectors, let us first remind ourselves of what covectors are. So gradients and covectors. The idea is, okay, if we have something like a derivative of a function, we can write that derivative of the function as the theta, the lambda, the f, the theta. So we write that as the vector and then derivatives of f. So we've done that quite a few times already. But now we realize that this looks very much like a scalar product, something like an invariant product. So we have another way to interpret this object here, a reinterpretation. In which we write this object as being df d lambda, which is like the gradient of the function taken along in the direction of the vector. So this is what a directional derivative is, right? You take the gradient and you take the component along the vector. We're going to write that as the gradient of the function f. Now this is taken here as a functional meaning something that is a linear functions on vectors acting on the vector V. So this is what defines this functional gradient. So this is a linear function of vectors. So we define the gradient in such a way that when it acts on a vector, it produces the directional derivative. The important thing about this is that it's supposed to be a linear functional when it acts on this particular combination. This is a linear superposition of the various components. Then, being linear, the numbers vi just come out, and now we're going to have the action of the gradient of f on the particular vector, basis vector ei. Let us proceed further. If we consider this guy acting then on this particular basis vector, what do we get? Well, if this were to be, let me see, there are several things that I can do here. Yes, if this were to be a particular, the f you put there is arbitrary. If you were to choose the function theta j, then this guy here is the gradient of theta j acting on the vector ei. And what this would give you is, what is this? This is interesting. This is, let's look at the definition. The gradient of f acting on a vector gives you the directional derivative. So here this would give us the directional derivative of the function theta j in the direction, the derivative with respect to lambda, but the derivative with respect to lambda, when lambda is the curves defined by these vectors, is going to be precisely theta j. This vector is tangent to the curve theta I be increasing while all the others are kept constant. So that's what this is. This is the tangent vector. V is the tangent vector. This is the tangent vector of that curve. And this, of course, is theta, it's a Kronecker delta J I. So what this is telling you is that these objects here, the gradients of the coordinates, happen to be such that they are duals in the sense of the basis vectors, in the sense that this is zeros or ones. Okay, that's one interesting comment about these functions here. The other is that, let's continue. Because this object here is a gradient, the gradient of the function theta, we can write this as being the derivatives of the function f with respect to theta, and then give the gradients of the coordinates. So written in this way, we see that whatever this object here is, it is an object that has components, and these guys are the basis. If this is a covector, these are the basis covectors such that they are dual to the normal basis vectors. So components of gradient f basis gradients. Okay, so now we have the following little trick to be performed here. Just like a displacement is or a velocity is the standard, the prototype of a vector, and we invent bases, and the vectors are components that transform in exactly the same way as displacements. Here we're going to invent covectors. A generic covector is going to be an object that has components and is expressed in terms of the basis covectors. So this is a generic covector. And what's important about these objects here is that when you change coordinates, from theta I to new coordinates theta I, the components of the gradient are going to transform in such a way. Remember what this is, the theta I. This we can write as the theta I prime, the theta I prime, the theta. So these objects here transform with a certain matrix. These indices downstairs, the order of the indices is given immediately by the location. If it is downstairs, this index here, which is upstairs in the denominator, counts as being downstairs. And the gradients, the basis covectors, which have index upstairs, transform in the opposite way. So this is going to be the I the I prime, yes, the theta R prime, in such a way that omega is invariant. The covector is invariant under changes of transform of coordinates, and this is exactly the same as for vectors. So these are important objects because themselves, the covectors are independent of the coordinates. Is there anything that I should be saying here? Well, let me write it out. It's something like this: components, basis, components, basis. Very good. Time to stop. Once again, why do we care about vectors and covectors? Ultimately, the reason we care about vectors is because they're going to be velocities. They're going to represent velocities. In any form of dynamics, that's crucial. The reason we care about covectors is because gradients are covectors, and inevitably we're going to be dealing with gradients of some form. We want to see how things change. But more immediately, covectors are the objects that describe momenta. Vectors are velocities, covectors are momenta. That's why in quantum mechanics, the momentum is an operator, and it's described by a gradient. It's because it is a covector. This is where things come from. But look, notice that what we're doing here has nothing to do with physics. This is just the geometry of these funny spaces and the vectors and covectors that you could put in the tangent spaces. So, time to stop now. When we come back, we're going to introduce the next level of structure that we need in order to do useful physics. See you then.